Good morning, everybody. Good to be here. Let me get a show of hands just so I can get a feel for what the audience is. Who's familiar with space or anything kind of along those lines? Okay. How about engineering, building things? Okay, cool. All right, so let's go ahead and get started. All right, so like we talked about, what I'm going to talk about is a few different things here. I'm going to talk about space in general, then talk about the space industry, kind of what different things people will do with space, then talk about telecoms specifically, so how you communicate from point to point, how you use satellites or other things in order to do that. And then I'm going to talk about how to get involved. So how to get involved with perhaps. There we go. How to get involved with whether it's space, whether it's new space, whether it's telecoms, anything like that. Already went through my background here, but currently a co-founder at Astronis. Previously, I'd worked at Planet Labs and then worked at a bunch of other names that you guys may or may not be familiar with throughout the space industry, building rockets, things that launch things into space, building various different other types of satellites and other things that do serve different markets in the space industry. So first of all, just a little bit more about Astronis. This is actually a picture of our demo satellite. This is what's called a CubeSat. I'll get into a little bit more later what a CubeSat is versus what other types of satellites are. But it's basically a small satellite that you're able to use that's relatively inexpensive to be able to launch. And it's very small, meaning it's also relatively inexpensive to build. Compared to traditional satellites that are very big and incredibly expensive to launch. I'll actually show you guys later a little scale factor so you can get a feel for what a CubeSat looks like, which is about this big. So not that, pretty much to scale here versus what a traditional satellite is, which is the size of a school bus. So Astronis is building lots of these, lots of the slightly larger satellites, actually about the size of a dishwasher, in order to serve telecoms applications, basically dramatically reduce the cost of providing access to space, or providing access to space and telecoms. But I'm not going to talk too much, at least at the beginning here, about Astronis specifically. I want to go through and tell you guys kind of some background. What is space? What do you use it for? How do you use it? Things like that. So I'm a big fan of kind of starting from first principles and giving people a feel for kind of the why of things, as well as kind of where all that came from. So I'm going to step back quite a bit, actually, and start to tell you guys a little bit about space. Specifically, I mean outer space. Obviously, space means lots of different things. The air that is between us, things like that are all space. But outer space is specifically things that, as is generally defined, things above what's called the von Karman line. The von Karman line is this kind of imaginary line that's 100 kilometers above the Earth's surface. And above that is called outer space. Below that is, I guess, just the atmosphere. So what you can see over on the right is just a view of the different, kind of what the atmosphere looks like going up, different weather, where aircraft will generally fly around here. You're flying in planes. And then significantly above that is 100 kilometers. Above that, space. Just for reference, here's where the space station is and where the shuttle used to fly to take people to the space station. So something that you guys are probably familiar with. Generally, quite a bit above that is actually where most satellites operate. And I'll show you guys a little bit more about that in a little bit. What space actually is, the environments are pretty extreme. You generally, well, there's very little atmosphere. There's actually no atmosphere. Atmosphere decays exponentially as you go up in altitude. And so there's a little bit there, and actually there is drag. So the space station, for example, actually has to keep boosting its orbit every few years or so. Otherwise, it would come in and re-enter, because there is actually still drag up there. It gets very hot. It gets very cold. Now, temperature is actually nothing more than the motion of molecules in the air. As a result, there is no technical temperature of space. There's only the temperature of a thing that's in space. So if you have, say, a person that's in space, you're getting irradiated, you're getting sunlight put on you from the sun, and then your body is then radiating energy out to deep space. And then there's a balance of energy that happens to you, and then that determines your temperature because you are made of molecules. However, in space, there isn't a temperature in the same way that there is air in this room that has a temperature. That said, any of these particular bodies can experience extreme swings, easily in excess of 100 degrees Celsius, easily below minus 100 degrees Celsius, whether you're in orbit, whether you're on, say, the moon, or any other bodies that don't have atmospheres that are able to provide regulation of temperature. Let's kind of zoom out a little bit here, talk about what is the scale of space. So when you're used to seeing pictures of things like the Earth or planets or anything like that, you're used to seeing things kind of lined up, like, say, this, where you've got the planets that are just next to each other, and it actually looks quite small. In reality, and similarly, you'll see the sun kind of sitting next to planets. This is actually the planet sizes to scale. This little guy right here is the Earth. So everything that we're on is this guy relative to some of the larger gas giant planets, and then the sun, which doesn't even fit on this picture. So just to give you kind of it's nice to sometimes step back and get a feel for what is the scale of space. Similarly, if you look here, this is showing you the relative distances of the planets. So again, here's where we are. Here's where the sun is. Seems kind of very far away to us, but it's actually, if you look at the solar system, it only scales down to this, and then the other planets are all the way out here. Again, taking the size of the planets into perspective of this, if you guys can read this, you'll notice that the sun on this scale is 0.2 pixels. So even the sun, which is huge, is less than a pixel. Like, you can't even show the size of it on this scale. So we'll zoom back in on this in a little bit and show the size of orbits. And even when you're talking about things that are orbiting the Earth, it's still very large, which is something important to consider when you're dealing with space, particularly when you're dealing with space exploration. And we'll talk about that as a future industry in a little bit, about going to Mars, going to the moon, going to asteroids, things like that. Zooming out, a little bit less practical for our purposes, because it'll be a while before humanity is doing really a whole lot out here. This is what's called a logarithmic scale, which means that it's actually the exponent. So instead of having 1 meter, 2 meter, 3 meter, it's actually 10 to the 1 meter, 10 to the 2, 100, 10 to the 3, 1,000 for every one of these that's going out. And again, you see sun, and because the Earth is looking much farther away, because this is logarithmic, and then just going out to all the planets, and then just what's outside beyond the solar system. Similarly, where we are in the galaxy. So why is space important? Why do we care? Space seems like it's pretty far out there. It's hard to get to. It's expensive to get to. But why do we care about it? So I just wanted to show a few pictures here of things that are relevant, at least terrestrially, things that actually could matter a great deal to you guys, and that's part of what is currently being used in space. So the first one on the top left is actually not something you guys are really using all that much, but it's just exploration. People going out, learning things, science, or even national or company or whatever pride of putting something into orbit. But there's a lot of actual science and things that people are learning in a microgravity environment that's actually important for bringing it back down to terrestrial life. In the middle here, shown basically agriculture. There's actually a lot that you can learn from looking at kind of large scale of what's happening to crops, and looking at different parts of the electromagnetic spectrum, visible light in particular, infrared light, and using that to track how things are going. And then you can decide how you're going to change your crops based off of that. Whether you're not watering them enough, whether you need to feed them better, things like that. And it's much easier to do that from orbit because you have a much bigger scale than if you're doing it from, say, drones or balloons or anything like that. On the right, TV truck, it's actually most TV trucks or any other people that are putting up any sort of high bandwidth data, they actually do that directly to satellite. They don't plug into a fiber on the ground or something like that. It's just easier to actually shoot it all the way up to orbit and then back down to somewhere else. Satellite TV is a big thing in many parts of the world. Obviously, your navigation, GPS, is something that uses satellites, so you can actually know where you are. knowing where even bigger things, tractors, ships, anything like that, all of their navigation is done not only using GPS, but also their communication is done using space, because you're in the middle of an ocean. There's nothing around you. As a result, the only way that you can communicate is through satellites. A huge amount of telecom, a huge amount of internet service is provided via satellites, again, when you're in areas that do not have access to fiber or other access to internet. And then just kind of satellite phones as well. So currently, there's a number of what are regarded kind of hot commercial sectors for space, and that's what I've shown here. So that if you go and look in the news and see what is space doing, what kinds of products are being made, what sorts of things are done with space, these are likely to be the 4 things that you'll hear about. First one is space tourism, is on taking people, putting them into suborbit. So if you remember, this line, this is actually a space tourist sort of trajectory. We're just going up into space. You're spending like maybe 5-10 minutes, and that's in a kind of microgravity type environment. You're able to see space. You're able to see the curvature of the Earth. You're able to spend a little bit of time in microgravity, maybe do some experiments, maybe just experience it. It's kind of like flying in a zero-G airplane, but more extensive. So that's one of these big things that was projected almost 10 years ago to be this big thing. It actually hasn't really taken off all that much, partially because A, there's kind of a limited number of people that are willing to pay a huge amount for it, and B, there's all these kind of smaller companies, particularly in what's called the Mojave Desert, that there's essentially a spaceport there and a whole bunch of companies that have actually mostly shut down. The only one that's left is actually this guy, Virgin Galactic, Richard Branson's company. But still kind of a relatively hot topic. Second one is launch. So launch vehicles, we'll talk a little bit about that more in a little bit, but launch vehicles is how you get to space. Obviously, it's very critical to any sort of space activities, particularly with SpaceX lately. This is something that's been undergoing a great deal of disruption. There's also small rocket launchers as well that are aiming to provide services that didn't exist also. The third one is remote sensing. So most notably known as visible sensing, so taking pictures of the Earth and then sending those back down, the sorts of things that you see on your satellite imagery on your phone when you look at Google Maps. That's actually not only from satellites, it's also from other above ground things, airplanes, drones, balloons, things like that, but a lot of it's from, especially the lower resolution stuff, is all from satellites. And then, furthermore, what I mentioned before about agriculture, looking in other bands, whether you're talking about radar, to look at the heights of things, look at the profile, terrain, even below ground, you can actually do that with sufficiently long wavelength waves. Or looking at infrared, or looking at ultraviolet, there's different things that you can see on different parts of the spectrum. So that's a big industry. And then the final one is telecoms. So taking data from one point to another, whether that's internet, whether that's TV, whether that's one of any other different things, telecoms has always been essentially the largest, other than perhaps launch, but certainly the most profitable of the space industry sectors. So let's talk a little bit about satellites. So satellite is actually a relatively generic term. All that satellite actually means is a body that's orbiting another body. So the moon is, namely the moon around Earth, is a satellite of Earth. Here's a picture in the middle that's actually all of the existing satellites and space debris. Obviously, not to scale because space is big. These are all actually, they might be big, but zoomed out to this level is actually, you wouldn't see any of this. So it's false rendition, not that we're taking a picture of that anyway. But every single one of these things, whether it's a discarded rocket stage, whether it's a pen that some astronaut let go, which somebody did on the space station did let go of a tool bag not too long ago and just kind of floated away and became another satellite. So any of those intentional satellites, anything like that, are all satellites. And then just to show kind of the biggest range of scale, probably the biggest man-made satellite of Earth is the International Space Station, which you see up on the top right. And then in the bottom right is among the smallest of satellites around the Earth, at least intentional satellites, which are CubeSats. And so those are actually doves, some of the CubeSats that Planet Labs, where I used to work, had put up. Now to give you a feel for satellite form factors, as I mentioned before, CubeSats are a relatively inexpensive satellite that you can build and launch, versus the traditional satellites, traditional telecoms in particular, also true for traditional imaging satellites or anything like that, are huge. So we've got a scale here to put you guys in perspective. So we've got people, and then the rest of these pictures are actually to scale, roughly that I could do by eyeing it. So you've got traditional telecom satellites on the right, size of at least a large car, if not a small bus. And you can see the people there. These are what are called microsatellites. This is the size of spacecraft that Astronis is going to be building that we started designing. We've built this as a demo satellite, and now we're building these for our production payload. These are also the sorts of satellites that a company called Skybox that you guys may have heard of, an Earth imaging company, has built in order to do their imaging. These are relatively popular because it's easy to get what are called ride shares, meaning you don't have to buy a whole rocket yourself. You can actually get a hitchhiker slot on somebody else's rocket and use that to go up and take you to orbit. So these are what are roughly 1 meter cubed and less than a couple hundred kilograms. So very small compared to the 4 metric ton and I don't know 6 by 3 by 3 or something meter traditional satellites. And then this is a CubeSat. So CubeSats are 10 by 10 by 30 centimeters. Seems very small. There's something that were considered toys for the longest time, or things for students to be able to learn. And then technology advanced, and it actually became possible to put enough power, put enough computing capability, put attitude control, put all the things that you need in a satellite into this form factor that's this big. And then they took off, and that's why there's now a lot of different companies, particularly remote sensing companies, that are using CubeSats. It's much harder to use that for some sort of a telecom satellite. So when you're doing telecoms, whether it's the people that are doing it in low Earth orbit or people like us that are going to be putting them to geostationary, generally go for something a little bit larger. So just to give you guys, again, a feel about orbits. So these orbits are to scale. So we've got the size of the Earth, has a radius of about 6,000 kilometers. And then we have the different places where satellites can be. Now, all of the different orbits that you're used to, whether it's the International Space Station, whether it's these orbits that all these remote sensing satellites are going to, they're actually all the way down here, just barely outside of Earth. In fact, no human has, ever since the Apollo missions, when humans went to the moon, no human has been outside of this for, whatever that was, 40 years or so. And I'm sure that'll change soon for a number of different reasons, but just to kind of, again, put things in perspective. And the reason that the Earth imaging satellites are so close is because of resolution. So imagine that you want to be looking at something. You want to be close to what you're looking at if you want to get any sort of good view. If you want to get a general kind of wide angle view, you might go up higher. But if you want to be able to see things that are useful, then you want to be actually pretty close to the ground. As compared to things like GPS, and Galileo, GLONASS, and Compass are all similar type, actually just different companies' versions of GPS, which is an American constellation. Those are a little bit higher because you don't want to have basically if you put GPS at the very low orbit, you need to have 1,000 satellites in order to put it up. As a result, you push it out farther, so that way you need less satellites. Makes it a little bit harder, but GPS is such a low data rate application that you basically send these tiny little bits of data, and even though it's farther out, it still works out okay. Compared to geostationary orbit, which is at 35,000 kilometers out, at the kind of upper end of what's called high Earth orbit. These guys were called low Earth orbit. These called medium Earth orbit, very original, I know. And then geostationary. Now, the nice thing about geostationary, so it's kind of annoying because it's really far away, which means that it's hard to close your link budgets. It's a very long distance, and anything spreads. So if you're doing communications, you have something called the inverse square law, which you guys are probably all familiar with, which means that any sort of energy, including radio energy, will spread out as it goes through any sort of distance. So it's really far away, which means that you have to have a much better receiver on the other side to be able to hear it. The cool thing about geostationary, though, is that what happens is that you orbit at the same rotation rate as the Earth rotates. As a result, you stay over the same part of the Earth at any point in time. So if we have a dish that's on our roof that wants to give us internet, then there's a satellite that's going to be right there. And at all points during the day, the satellite is always right there because it maintains the equivalent position within the reference frame that is us standing on the Earth, which is very handy because you don't want to have tracking dishes, which are much more expensive. Again, talking about scale, because I like putting things into reference to give everybody a feel for kind of what things actually look like in reality. And it's hard to remain in perspective when you're looking at numbers, just because of how our brains work. So here we have the Earth, a low Earth orbit, where most of these satellites, most things that we do are located only within here. And you go all the way over here, and that's where geostationary is. So it's 6x farther away from the Earth than the Earth's radius or a low Earth orbit. Then the moon, just for reference, is then 3x further away than that. Or actually 6x, another 6x farther away from where geostationary is. So when you think about, again, referencing back to, say, Apollo, why it took days of actually putting a significant burn to put you into a trans-lunar trajectory, and then it took multiple days in order to get there. And then again, if we think back to what I was showing before about how far the planets are apart, and those are actually the planets in their orbit rings, so the planets could actually be even farther apart if they're on the opposite sides of the sun from each other. Why the notional transit time to go to, say, Mars, our closest planet, is 8 months. So, yeah. All right, how do we get to space? We talked about all these cool things that we can do with space, and what those might look like, what satellites are, but how do we get satellites into orbit if they're not already there? So we use things called launch vehicles, basically rockets, which are basically controlled explosions. So you take a big bunch of very explosive compounds that will, when you make them touch each other, they will make a big explosion, basically a bomb, and then you put a nozzle on the end of it, and then that results in the bomb sending you in the other direction, basically by Newton's second law. So you push something one way, you go the other way. So the way that looks, you launch, you then go up for a little bit. You actually go up for a little bit just to get yourself out of the atmosphere, and then you kick over and you go straight. You go horizontal. Now the reason for that is that getting to space isn't about going up. As we looked before, we saw that we don't need to go up very much to go to space. We mostly need to go horizontal. So what orbit means, orbit is just going so fast that as you fall, you keep missing the Earth. So the Earth is round, so you keep going forward, and you keep falling, but you happen to be falling at the same rate that you're just missing the Earth as you're going around. Now, as it turns out, you need to be going quite fast for that. You need to be going about 8 kilometers per second for a low Earth orbit. So, and to put that in perspective, for that suborbital trajectory that I showed you guys before, the amount of energy necessary to achieve that trajectory, that ballistic trajectory, versus the amount of energy that you need in order to go into orbit is about a 10x, a factor of 10 different amount of energy, which is why it's so much harder to go actually put something even in orbit, even in a low Earth orbit, even something relatively small. So not an easy problem. Just to show you guys some more figures, this would be an example launch trajectory. You go up a little bit, and then you kick over and start going horizontal. And then similarly, an actual launch, this is a long exposure picture showing launch and then going into the curved trajectory. That's called a gravity turn. Gravity turn, by the way. If you are listening to any sort of launch broadcast or anything like that, you'll hear that. Oops. Just showing a couple of different rockets here. That's an Atlas V, kind of one of the more traditional type rockets. Something that was made by a company, or is made by a company called United Launch Alliance. They've been working for a very long time, have had many different rockets with no failures, and they're kind of the traditional go-to rocket company. On the right, we've got SpaceX. Who has heard of SpaceX? Okay, just want to check. So SpaceX on the right, new upstart with building rockets, actually been around for quite a while now, but at this point they're starting to get the cadence to be going up. have reusability, things like that. So pretty important there. This is just showing a bunch of different other types of rockets. There's actually lots of different rockets that are available from different countries, and probably not much reason for us to go into that at the moment right now. Some current, upcoming, and existing innovations in launch. So launch sucks. You're basically expending this chemical energy in order to put us to the orbit. But back on these rockets, so the payload is actually like this, and then your rocket is this. And that's because of something called the rocket equation. The rocket equation, and it's exponential. So you have an exponential, and you have a tiny little mass divided by your total mass, and that determines the amount of delta V that you need, change in velocity, which, as I said, was 8,000 meters per second, which is a relatively big number to be putting into that exponential mass fraction. As a result, even with a staged rocket design, you're looking at getting maybe 10%, probably more like 5% of the rocket's total mass is your payload. So this is a problem. There's not a huge amount, and beyond that is we have to throw the rocket away every time we use it. And so as Elon has put it many times in public description, it's like every time you want to drive somewhere, you toss the car after you use it. Or every time that an airline flew somewhere, it would just send the plane to the junkyard after it uses it, which is unfortunate, which is why he's been going and using reusability, which actually managed to achieve by landing the first stages, landing the Dragons, potentially even landing the fairings that are around the satellites as well. In the middle, I just got a picture of one of these nano-launch rockets. And on the right, have something called Skylon, which is it's a company called Reaction Engines. And they're looking at building air-breathing propulsion, meaning that they actually use a jet, kind of like what aircraft use. And that's how they get a lot of their delta V, using the air. So the reason that an airplane is so much more efficient than a rocket is that a rocket has to carry both the fuel and the oxidizer with it, whereas an airplane only carries fuel, just like your car does. And then the oxidizer is that it pulls in oxygen from the atmosphere and uses that. Now, the oxygen tends to be, A, very not all that dense, and B, kind of abundant. So if you're able to just burn your fuel like an airplane does and then pull in oxygen, you can be way more efficient. Now, as you get higher and higher, there's less oxygen, so that becomes not a viable strategy. But there's some concepts that people are looking at, which I personally think is kind of the way of the future once we get there for launching things, to get as much as you can initially by using the atmosphere to give you your oxidizer, and then switch over to traditional rocket mode once you get higher. But hopefully you've built up a lot of your energy by that point. Go a little bit into some of the different challenges of rockets or of the space industry in general. So one of the things is regulatory emissions. So in geostationary, when you're in the geostationary arc, it's very regulated what frequencies you can be using and where you can be beaming different frequencies to the ground. As we said before, you're going a very long way. As a result, receivers need to be very sensitive. And because of that, you need to make sure that you're sufficiently outside of any frequency bands that you're not interfering with somebody else. So there's an organization called the ITU, which regulates these things. It's actually a very big deal. It's almost like kind of like buying web domains in order to get access to these. People like grab them, and then they'll squat them, and then they'll have them kind of for time. Something called ITAR, International Traffic in Arms Regulations, and EAR, Expert Arms Regulations. This is a big issue. This is the result of frankly, US government thinking that a satellite is the same thing as a cruise missile, and therefore being afraid of any sort of technology that goes into a satellite, resulting in other countries learning how to build cruise missiles. So it's really silly, but it's a really big deal for companies that are building space hardware in the United States, because it means that you have significant restrictions on people that you can hire, and it means that you have significant restrictions on components that you can buy, what you can talk with, what rockets that you can use, and what sort of exports you can do. Environmental extremes, like we talked about before. The components in space will get very hot, very cold. When you launch something, the environment is very extreme. It gets shaken really hard. So being able to design around these sorts of things is very challenging. Radiation. The Earth has, or humans have evolved within the Earth within the protective shell of the ionosphere, which has allowed us to become who we are, and allowed us to shield us from a lot of the sun's radiation, or galactic radiation, or total background radiation. Once you're outside of the magnetosphere, you no longer have that anymore. As a result, you have to deal with a lot of that. And the components that you're used to, that we have built to work in Earth, don't necessarily work up there either. As it turns out, a lot of components actually do, and that's one of the kind of new things that's been coming up lately, is learning how to use those components and figuring out which ones will work in space, which ones will not. Jumping ahead, looking a little bit at the future, what are potential things that are coming up to kind of get your brain juices flowing of what, if we want to get involved in space, what might be coming up next. Some of these things are mining asteroids, building habitats in orbit, building habitats elsewhere, finding reasons to go and live on Mars, making that economically viable. The biggest challenge to all these things is, A, that it's really hard to get there, really hard to put enough hardware there and be useful. But there is actually a great deal of promise of potential things that we could achieve with sufficient technology. All right, let's talk a little bit about telecom satellites specifically. So what do telecom satellites do? I described before, you're basically taking information from one point and sending it somewhere else. Whether that's taking it from a place that has internet, sending it to a cell phone tower, and then people can all then access internet through the cell phone tower. Whether you're just taking it point to point from one business to another, giving people internet, doing a direct broadcast, giving people Wi-Fi in an airplane. All these different types of things that revolve around getting data from one place to another. These all actually use the same sort of standard in terms of, so you can use actually the same satellite hardware in order to provide all of these different services. And yep, covered all those. So let's talk a little bit more about the technical bits of how you build telecom satellites. So this is just showing the electromagnetic spectrum that you guys are probably all familiar with. Radio waves, microwaves, which are the types of waves that are in your microwave, but are also what are used for nearly all communication, the same wavelength. Going up to visible light, ultraviolet, X-rays, gamma rays. So high frequency is really difficult for us to be able to deal with our current technology. Certainly doing anything other than light is difficult to do at visible. So we're really looking at the microwave, the radio spectrum for anything that we do communication with. And generally speaking, we've been going from low frequency to high frequency as technology has been advancing. So a lot of remote control type things, radio in your car, which, I don't know, maybe you guys have heard of that. It's not really being used a whole lot lately. Cell phones are all relatively low frequency. And then a lot of this satellite communication is being done at somewhat higher frequency. And then you kind of keep going up from there. And this is really where a lot of satellite telecoms are being done. The reason for that is that although path loss, the amount of loss that you incur by going from point to point in space increases with frequency, also does the gain. The amount of energy that you can, the amount of directivity that you can get out of a dish of a given size will increase linearly with frequency. As a result, if you have a pointy dish on one side, a pointy dish on the other side, then you can get linearly increased data rate as frequency increased. So kind of more bang for your buck for a certain amount of power. I'm just zooming in here to satellite frequency. If you're looking at satellite telecoms, you'll hear terms like L, S, C, X, KU, K, Ka band. All these are delineations for different ranges of frequency. So for example, L, S, and C are typically kind of telemetry data downlink type frequencies for different satellites. Things like KU, K, Ka are generally more for the sort of internet providing, TV, broadcast, things like that. Geostationary satellites, like I said, are on the geostationary arc. And the only reason I put this up is I wanted to show kind of the regulation. So satellites are assigned a specific slice of the geostationary arc, which is defined actually by the frequency they're using. So as frequency goes up, it becomes more directive, which means that you can pack satellites closer together. Again, this has a radius of 35,000 kilometers. So the satellites physically aren't like touching or anywhere close to touching each other, but it's all about the energy that you have to get up to them. So if you have a dish on your roof, you want to make sure that that energy on your dish that's broadcasting up to the satellite is only going to hit the satellite that's intended. You don't want to hit the neighbors. And so that's what drives how close you can pack the satellites together on orbit. Just a little bit about the satellites themselves. So just to give a kind of a picture of what relay looks like, you have one ground station, a destination ground station or user terminal. You take energy up. So traditional satellites, what they do is they take in one set of energy, one set of frequency, and then they just turn it back around. They have literally a pipe. It's called bent pipe because they take energy from one place, they amplify it, and they shoot it back down. What we're looking at doing is actually a little bit different. It's about cleaning up the noise, then amplifying it, and then shooting it back down, which has a lot of advantages. But traditionally, it's as simple as that it's basically a pipe that's just turning it around. This is an example of SSL is one of the satellite manufacturers. I just saw this diagram on Google image search, so I know it's OK to show. Basic ideas of a telecom satellite, power. You're basically turning power into microwaves, is what a telecom satellite does. Solar panels to collect a lot of energy, reflectors to take in energy from the ground, amplify it, and send it back down to a different part on the ground. This is the short version of how a telecom satellite works. So traditionally, like I said before, you have a gigantic satellite that a contractor builds, somebody like Boeing or Lockheed Martin or Space Systems Loral. Now, these are really big, these are really, really expensive satellites, $500 million to build it, and then another couple $100 million to launch it. So people don't generally have that sort of money lying around. So what you typically do is you have this middle group called a satellite operator. That satellite operator basically goes in and finances the whole thing. They pay the manufacturers to build the satellite, and then they run a whole bunch of different statistics and decide that this is the right investment to be making for the right market and things like that. And then they own the satellite after the satellite manufacturer builds it, put it on orbit, and then customers are able to use it, and then the operator just kind of rakes in the money. So this is really the only way that it can make sense when you're dealing with things that are the better part of $1 billion to put up a single unit of spacecraft. I mentioned before there's different ways that you can provide internet. You can provide telecom services. Geostationary satellites is obviously one of them. Fiber is another one. Fiber that's just laid in the ground, laid under the ocean to go from point to point. But a lot of the world doesn't have that. There's a couple other concepts that are being used. There's low Earth orbit constellations. There's two of them. One called OneWeb, one called SpaceX, or one that SpaceX is also putting up, that are looking to put up actually a couple thousand satellites per constellation, which is a lot of satellites. There's a lot of technical challenges with that. It's not really worth getting into too much, but it's another concept that's out there. And then the other one is to put things closer to the ground. Drones, balloons. You guys have probably might have heard about Google Loon or the Facebook drones. That Facebook drone test flight was pretty recent, I think a couple weeks ago. But these are all the different options that you can use to provide telecom services. So talking about kind of Astronis or any other of these new space companies, Planet Labs, where I used to be, how SpaceX works, anything like that, how do we do things differently? It really comes down to two different things. Number one, using non-traditional components. Traditionally, when you need to have a microcontroller, just a tiny little device that's actually way less powerful than what's on your phone, you buy this component that is rad hard, meaning that it's a space-grade component that's been designated to be proven to be working in radiation. That little microcontroller, which is, again, an order of magnitude, or actually probably about 2 orders of magnitude less powerful than your phone, costs $200,000. However, it's equivalent to something you can buy on any just normal electronics website, if you're familiar with like DigiKey or something like that, and that costs $20. So you have things like this that are many orders of magnitude cheaper to use an off-the-shelf component. Now, it's not designed for space, but if you're careful in how you pick it, how you use it, how you shield it, you can actually use these components in space. And that is a game changer for cost and what things can make sense and doing things in a different way. Second one is assembly line. Satellites are traditionally, every single satellite is a very special snowflake. It's completely different. So you might think these traditional, like a Loral or Boeing or whatever, yes, they build these different satellites and they have a bus that's sort of similar, meaning the thing that supports the payload supports the dish. But the payload, the dish, the transponders is completely different. It's like artwork every single time they do it. And that makes costs stay really high. And so the sort of approach that we've been taking, the sort of approach that Planet's been taking, that a lot of these companies have been taking, is doing these sort of data storage or RAID approach. RAID is a term for hard drives, where you put multiple hard drives in your computer, and they both have all the same data. So it doesn't matter if one of them craps out. So you can use lower quality hard drives and you have redundancy in the system. So the idea is that we build lots of smaller satellites, and that because they cost so much less than the big satellites, we can then take different risk profile with them. It's okay if some of them fail. And because it's okay that some of them fail, we can now make them sufficiently cheaper. The exact opposite of this is how space is so expensive. You build something that's going somewhere hard, it's hard to get there, it's expensive to get there, and then therefore it has to work, and therefore it has to get more expensive and more risk intolerant and things like that. So if you turn that on its head and you go with lots of smaller things, the game changes dramatically. And so that's essentially what we're doing, is taking the big satellite, replacing it with lots of little ones. I think I mentioned before, basically what makes this possible, commercial off-the-shelf electronics, battery technology has been growing by leaps and bounds lately. Solar cell technology has been improving dramatically. Thruster technology, propulsion, has been improving dramatically. And then shared payloads is also a relatively new trend that's been going on. So that's another thing that makes putting up these smaller satellites possible. So what this means is that we can basically crash a lot of these telecom markets, provide internet services, telecom services in a way that has not been provided before for much less money. And that enables us to A, serve new markets, B, create new markets, C, serve areas that just couldn't have afforded it in the past. I'm going to actually skip through these ones and jump up to how to get involved. So we talked all about kind of space industry and space in general, what kinds of things have been going on in the past, what kinds of things are likely to be happening in the future. And the question that some of you guys might be having is you want to be interested, you want to get involved in the space industry or something related to it. How can you? Or does that even make sense? So I think we can jump into a little bit on the reasons that you might want to get involved. This might be true. This is certainly true of other business areas as well, but I think it's certainly true for the space industry, especially if you're working for new space companies. And a lot of this is actually foiling new space companies versus traditional space companies. It's incredibly dynamic and fast-moving. You wouldn't think that about space. Actually, you might think of that about space if you're not familiar with traditional companies, but traditional companies are not. They're incredibly slow and using incredibly old technology. If you're working for, again, small companies, you have the same sorts of things. You gain a lot of responsibility. You have an opportunity for an incredible amount of impact. It's incredibly challenging, I think so, more so than a lot of different other market sectors, which to me is very interesting. And it's also incredibly intense. When you're working towards a launch campaign, then you have a deadline that is incredibly hard. It's not like launching software where you might have a little bit more flexibility, or you might have an ability to do bug fixes afterwards or something like that. Once you launch your satellite, all the hardware is obviously completely fixed. You can't go out and service it. You can't do anything like that. Yes, you can over-the-air update it. You can update your software, but a lot of it is really tied to that very specific deadline, which makes it quite intense. Just some pictures that I tried to grab to show, none of this is actually necessarily satellite related, but you generally have, it's almost kind of controlled chaos working for any sort of small company, any sort of startup, but I think particularly true for things that are hardware, and particularly true for things that are space related. Because you have so much different hardware that you're developing at any point in time, testing all of it, figuring out what's going wrong, changing it around, and then just kind of changing what sorts of things you need to be doing. Especially when working for some of these complicated environments with radiation and the temperature extremes and vibration and things like that. You sometimes are going down one path and it's just completely not going to work. So you have to go completely switch to something different. So then what are we as an industry looking for? What sorts of things do we value? I think a lot of that comes down to, and this is just going off of, I've interviewed lots of people, and these are kinds of nitpicks, or not nitpicks, but sorts of things that I fail to see in a lot of people that I talk to. And when people ask me for advice on if they want to get involved with space, or even if you just want to get involved with hardware, or a lot of these I'm sure are true to just any company, period. But the sorts of things that I think are important, hands-on experience, you've done things yourself, you've built stuff yourself, you have an ability to build things. And this is certainly not limited directly to hardware. This is, or limited to engineering. This is just, you have an ability to make something happen, to go from idea and execute that into creating something is a huge deal that not everybody is capable of doing, or at least not everybody currently with their current set of tools is capable of doing. Ability to self-direct, to go find problems, solve problems yourself without having to be micromanaged. Ability to make trade-offs. So when you're in certain, depends on what sort of industries you're looking in, what sort of products you're looking at, the ability to just having to make hard trade-offs is not something that you necessarily always have to do. Particularly true when you have any sort of environment or any sort of industry that has so many different constraints. It's important to be able to make those hard trade-offs for, oh, well, do we have enough mass for this? Can we fit a cost budget? How about our power budget? How about ability to manufacture it or make it? Anything like that. Solid fundamentals are always incredibly important. The fact that you can just kind of hack something together is great, but knowing the fundamentals of whatever discipline you have is critical as well, because that allows you to actually go through and make the real trades, is knowing fundamentally why is something true. Ability to think creatively, and then just ability to fail and try again.
So what entails solid fundamentals? So like I studied electronics and telecommunications. I know sure, Ohm's law is the most fundamental thing like you could think of. And sure, there are some principles of like channel pattern, like encoding, like for communication and other things. So what would entail solid fundamentals? Because yes, I'm checking all the other boxes, but I don't know what's solid fundamentals.
Yeah, so to me, solid fundamentals means being able to go back to the first principles, the first derivations. So let's say that you are looking to find if this component is capable of handling radiation or not. Right. Knowing what is the structure of that component down to the transistor level, knowing what is the structure of that, and how are you using it, and kind of being able to dive as much as possible into things like Ohm's law and.
So like MEMS and how are MEMS created at the micro level, just having that knowledge, would that be a solid?
Yes, I would consider that to be a solid fundamental. Knowing that, knowing how that particular technology relates to the basic equations that you learned in first electronics classes, and being able to make those sorts of trades, I would consider to be solid fundamentals. All right, how to find a company to join, particularly if you're interested in space-related stuff. Anybody at larger companies will know kind of what the industry is, particularly if you're looking for larger companies, they'll know what that looks like. Going to conferences or just reading about conferences, going to a conference website and seeing what companies are listed. You can often find descriptions and go and search for things that way. Alumni connections that you have from anything that you've been going to, any sort of schooling that you've had, personal network, or even just looking at, say, space news sites, and I put a couple up here, and just seeing what's going on and what might be interesting to you, and then just kind of going down that link following chain of, hey, these are things that might be interesting, let's go look at this company's website. Oh, but this actually references another one, and then that might lead to places that you would find interesting. So I've got a couple slides here on how to start something yourself. I don't know what kind of the rest of your guys' curriculum is, but I understand it's mostly about entrepreneurship. So I suspect that this is going to match very closely with what you guys kind of generally learn about entrepreneurship, but it's possible that this might have a little bit of a twist from a space perspective. So how do you start something yourself? Really comes down to the right idea, right team, right time. It's no different in space than it is in anything else. And that's actually something that I think is important to kind of convey, that space isn't fundamentally, building stuff for space isn't fundamentally different than building something for anything else. It's just different boundary conditions. And some of those boundary conditions might be big deals, they might be hard, but taking somebody who has no space experience and then plopping them down into doing something that is space related is just a matter of learning a few different boundary conditions, a few different side experience and things like that. It's not changing fundamentals. The fundamentals of how something works is no different on the ground versus in space. How do you find opportunities? This again, I think, is very similar to what you guys are probably being taught about entrepreneurship from anywhere for any other sort of industries. Giving a slight spin on it for space-related stuff, following space news, seeing where pain points are. Hey, getting stuff to space is really hard, but maybe you have this idea of how you can do something differently that hasn't been done before. Or you're looking at Earth imaging, and maybe you have some other idea of something that seems like a really good idea. Again, just learning about industries, maybe joining an existing company, seeing what pain points are. Once you're actually doing something and building something, you see all sorts of ideas of things that are just completely broken, and you want to see a new way to do it. And then, again, just looking at things from first principles. One of the things that Elon posted about with rockets, I think, was going through and looking at what is the actual cost of a rocket in terms of propellant, the only thing that necessarily has to get expended. And that puts a floor on the cost of getting stuff to orbit. In reality, there's realities that make that not possible. But if you go and dive down to the very nitty-gritty details of just basic CAN calculations on something, then how does it fundamentally line up? And how does that compare to how things are currently being done? The bigger that gap, the more opportunity for an industry to be disrupted. How do you evaluate opportunities? Again, I'm sure this is very similar to what you're being taught for anything else. Talk to possible customers, learn what you need to build, learn the skills, learn the boundary conditions, how that's different than what you're experienced with. Find the right people that can augment your capabilities. Consider what's currently being done. Consider it. Don't necessarily do anything that way, but consider it at least so you know what the options are, what people have been trying. Prototype it, test it over and over again. How is starting a space industry unique, or a company in the space industry unique? I think I've gone through most of these before, but basically it comes down to a lot of things are long lead. A lot of components are. If you're going to commercial off-the-shelf components, COTS components, then that helps a lot, but certain things will still be long. Sales cycles are long, especially if you're dealing with B2B, business-to-business sales. It's a long cycle developing hardware and then putting it into orbit. Whether that's for testing, whether that's for deployment for service, those are long cycles and relatively hard to do. So you figure out what are shortcuts that we can take? What sort of testing can we do on the ground to short circuit our development cycles? Deployment schedules are often difficult to control because launch is often not something you directly have control of. Inability to access the product once it's deployed. When you're in space, it's hard to do that. It's out of a lot of people's experience, but again, that is not necessarily a reason to not get involved with something or for somebody to not get involved with something just because they're not experienced with space with those boundary conditions. And the final thing is that it's capital intensive. It's not as bad as it used to be. You don't need to be a billionaire to start a space company anymore. These days, you can go with the normal VC funding rounds. You can even, oftentimes, in certain cases, bootstrap something and kind of put together an idea for very little money, then go after contracts to get you rolling, and maybe you don't even need VC money. It's gotten to a point with small satellites that you can actually build stuff on not ridiculous amounts of money. And that's it.